Welcome back to Day 8. Today we crack open the engine behind almost all of today's most powerful AI, the neural network. Now, this is the part where a lot of explanations reach for terrifying math and lose everyone in the first 30 seconds. We're not doing that. I promise you, by the end of these few minutes, you'll have a clear, honest picture of what a neural network actually is and how it works. We'll even watch one light up as information flows through it, and then build a real one that solves a problem a simpler model just can't. Let's demystify the neural network. First, let's clear up the biggest source of confusion. Neural networks are loosely inspired by the brain. Loosely. The word neural comes from neuron, the cells in your head. And just like your brain has billions of neurons passing signals to each other, a neural network has lots of simple little units passing numbers to each other. But please don't picture a digital brain in there. It's not. It's a clever mathematical structure that borrowed one good idea from biology, lots of simple units connected together, and ran with it. No consciousness, no thoughts, just signals flowing through connections. So here's what a neural network really is. It's a big collection of simple units, often called neurons, arranged in layers. There's an input layer where your data comes in, one or more hidden layers in the middle that do the real work, and an output layer that gives the answer. Each individual unit is almost laughably simple. It takes in some numbers, does a tiny calculation, and passes one number forward to the next layer. No single unit is smart. The intelligence comes from how all of them connect and work together. Let me show you that flow in action. Okay, look at this. On the far left, in blue, is the input layer. That's where your data enters, maybe the pixels of an image. Watch what happens. Each input value gets sent along every connection to the next layer, and you can see the signals literally traveling down the wires. The middle layers, in teal, are the hidden layers. Each unit there gathers up all the signals coming into it, mixes them together, and passes its own result forward. The wave moves left to right, layer by layer, until it reaches the output on the right, in amber, which lights up with the final answer. That forward flow of signals, layer to layer, is a neural network thinking. That's the whole core mechanic. Now, here's the most important detail, the thing that makes the whole thing actually work. Every single one of those connections, those wires between the units, has a number attached to it called a weight. Think of a weight as a little dial that controls how strongly a signal flows through that wire. A big weight means that connection matters a lot. A small one means it barely counts. A modern neural network has millions, sometimes billions, of these weights. And every weight is adjustable, which leads straight to the magic question: how do they get set? And here's where it all connects back to learning. At the very start, all those weights are random, so the network is basically guessing nonsense. Then we train it, using the exact loop from earlier days. It makes a guess, we measure how wrong it was, and then it nudges every single weight a tiny bit in the direction that would make the error smaller. Do that across mountains of examples, millions and millions of times, and those weights slowly settle into values that produce great answers. So training a neural network is really just one thing: finding the right setting for all those dials. Learning is tuning the weights. So why do we stack so many layers? Why deep? Because depth is where the power comes from. Each layer builds on top of the patterns found by the layer before it. In an image network, the first hidden layer might just detect simple edges. The next combines those edges into shapes. The next combines shapes into parts, like an eye or a wheel, and so on, until the final layers recognize whole objects. A single layer can only learn simple patterns. Stacking many layers, that's the deep in deep learning, lets the network learn staggeringly complex things. Let me prove that depth really matters, with code. Here's a classic little puzzle that perfectly shows why those hidden layers matter. It's called XOR. The rule is simple. The answer is 1 only when the two inputs are different, and 0 when they're the same. It sounds trivial, but it has a famous property: you cannot separate it with a single straight line. That means a flat model with no hidden layer literally cannot solve it. A neural network, with just one hidden layer, can. Let's pit them against each other and watch. Here's the setup. Our data is the 4 XOR cases 0, 0, 0, 1, 1, 0, 1, 1 with the right answers. Then we train 2 different models on it. The first, linear, is a flat model with no hidden layer, just input straight to output. The second, net, is an actual neural network, and the key part is right there, hidden layer sizes of 8. That gives it one hidden layer of 8 units. Exactly the structure we just watched light up. Same data, same task. One has a hidden layer, one doesn't. Let's run it. And look at the difference. Go row by row. The flat linear model just gives up and predicts 0 for everything. It gets the 2 same cases right by luck, but completely misses both of the different cases. 50%, no better than a coin flip. Now the neural network. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. Perfect. 100%. The only thing that changed was adding one hidden layer of 8 little units. And suddenly, it can solve a pattern the flat model never could. That, right there, is the power of depth. Sit with that for a second, because it's the whole reason deep learning took over the world. We didn't use more data. We didn't use a cleverer algorithm. We just added a hidden layer, and a problem that was literally impossible for the flat model became easy. Now imagine that effect, but with dozens or hundreds of layers and billions of weights, learning from oceans of data. That's how neural networks recognize faces, understand speech, and power the AI you talk to every day. And once you've got this, you understand the engine inside a huge amount of modern AI. Neural networks recognize what's in photos and help cars see the road. They turn your speech into text and translate between languages. And the large language models behind ChatGPT and Claude? Those are gigantic neural networks with an enormous number of layers and weights. When people say deep learning, this is what they mean, neural networks with many layers. You now know what's humming away under the hood of almost all of it. Let's lock it in. A neural network is a bunch of simple units arranged in layers, passing signals forward from input to output. It's loosely inspired by the brain, but it's really just math, not a real brain. Every connection has a weight, a dial, and learning is the process of tuning all those dials to shrink errors. And depth, stacking many layers, is what unlocks the ability to learn genuinely complex patterns, as we proved when one hidden layer cracked a problem a flat model couldn't touch. That's the neural network, no scary math required. So there it is, the neural network, demystified. Simple units, layers, weights, and the power of depth, and you watched one both light up and solve a real puzzle. We keep talking about training a network versus actually using it, and it turns out those 2 phases are wildly different. One is slow and expensive, the other is fast and cheap. That difference explains a lot about how AI works in the real world, and it's tomorrow's topic, training versus inference. Thanks for building with me today. See you tomorrow.